Welcome. This is a video presentation of the paper, Quantum Time is the time it takes for an elementary particle to absorb a quantum of energy. In the first hyperverse paper, we postulated that the universe was the three-dimensional surface volume of a four-dimensional hypersphere. Then we asked a question: how big would a hypersphere be whose surface volume matched the volume of the observable universe? To do this, we solve this problem. We take 2 pi squared r sub h cubed is equal to 4/3 pi sub o cubed. This term on the left is the surface volume of a four-dimensional sphere, and the term on the right is the volume of a three-dimensional sphere. R sub h is the hyperverse radius, and r sub o is the radius of the observable universe. Using a value of 46.25 billion light years as the current radius of the observable universe, we find the radius of this hypothetical hyperverse to be about 27.6 billion light years. So we take our terms, solve for r sub h, plug in our value for the observable universe radius, solve, and we get r sub h is equal to about 27.58 billion light years. We take that radius and divide it by the age of the universe, and we get 1.99 light years per year as the expansion rate of this hypothetical hyperverse. And that's twice the speed of light, or 2c. A 2c expansion rate is a fascinating result. Is it meaningful? We say yes. We developed a cosmology far more robust than the standard model. But there is a glaring issue. The whole universe is much larger than the observable. The whole hyperverse would be much larger than the observable hyperverse. The hyperverse model gives us a possible value of the size of the whole hyperverse. Using the concept of the geometric mean expansion of space, explained in detail in earlier papers and videos, when we calculate the geometric mean partner of the small radius, what we call the SRQ radius, we find that the energy of the whole universe is equal to the energy of the observable universe times a factor of r sub h over 2 LP to the fourth, where r sub h is the radius of the observable hyperverse and 2 LP is 2 Planck lengths. And as a review, as we did this in the geometric mean expansion of space paper, we use the geometric mean equation, and taking the smallest energy, the small radius quantum energy, multiplying it by what we'll say is the largest energy, to get the initial energy squared. And when we solve for this, we get the energy of the observable universe times this factor, r sub h over 2 LP to the fourth power. The SEQ, or small energy quantum, has an associated radius. If we take the energy of the observable universe and divide it by the energy of the small energy quantum, we find that we get this number of small energy quanta within the observable universe, r sub h over 2 LP squared. And this comes to about 10 to the 121 power. So we'll take the volume of the observable hyperverse and divide it by that number, and we get this equation here, 2 pi squared times this value here. Now this should be radius cubed, so we have to take the cube root of this. So the cube root would be the radius of the SEQ, and that can be expressed as this value here to the 1/3 power, or alternatively r sub h times 2 LP over RH to the 2/3 power. And numerically, it comes to about 6.5 times 10 to the minus 15 meters. Now, we did these calculations in the geometric mean paper, but for a quick review, the radius of the whole hyperverse would be essentially the cube root of that factor, or r sub h, over 2lp to the 4/3 power, meaning the radius of the whole or entire hyperverse is about 4 times 10 to the 107th meters. It's larger than the observable hyperverse radius, this hypothetical thing we just created, by a factor of more than 10 to the 81 power. So let us assume that the whole is larger than the observable hyperverse by a factor of r sub h over 2lp to the 4th power, and that the radius is larger by a factor of r sub h over 2lp to the 4/3 power, and look at the whole hyperverse using the now and then approach we used in earlier papers. Now refers to the size of the universe today, and then to the size when the universe was 1/2 the current age. This allows us to examine the effect of doubling. The radius of the whole hyperverse would increase by about 4 times the cube root of 2. And we do this looking at the radius of the whole now, we have this factor here, and the whole then, and we take r sub h divided by 2. Everywhere we have r sub h, we have to cut it in half. And that gives us an increase with a doubling of about 5.039. Since by definition the hyperverse radius, that's the observable hyperverse radius, doubles with a doubling, the whole increases by a factor of what we just calculated, and the observable by 2. So the rate of increase of the whole to that of the observable is 2 times the cube root of 2. With a doubling of the universe, the energy of the whole hyperverse increases by a factor of 32. Again, we take the energy of the whole divided by the energy of the whole when the age or size of the universe was 1/2 of what it is, and we find that the whole increases by a factor of 32 with each doubling. Looking at the energy of the observable universe now versus then, which we did also in the geometric mean paper, we find that the energy of the universe doubles with each doubling of the hyperverse radius, or with time. Now comparing that to the rate of change of the energy of the whole, we find that the energy of the whole is increasing at a faster rate than the observable by a comparative factor of 32 divided by 2, or 16. And the radius by 2 times the cube root of 2, or about 2.5. So we have a dilemma regarding the 2c radial expansion. The whole universe is larger than the observable, and we're thinking it's 10 to the 243rd power greater in volume and energy than the observable. And the radius of the whole is larger by a factor of 10 to the 81 power. Now the observable is part of the whole hyperverse, just a tiny portion of it, and it is the same age as the whole. Now we can calculate the radial velocity of the whole hyperverse by dividing the radius of the whole hyperverse, which is the distance, divided by the time. And we have this value here for the radius of the whole. We have the same age as the observable universe. And we find that the whole is expanding not by 2c, but by 2c times this factor. That means that the radius of the whole hyperverse is expanding at a vastly higher rate than the observable. For the observable hyperverse, we calculate a radial velocity of 2c, and for the whole hyperverse, we calculate a radial velocity of 2c times 10 to the 81. That is 2 different velocities for each point in space. Not only do we find 2 velocities for every point in space, one of which is wildly beyond our experience, we find that the whole radius is accelerating. Notice that the hyperverse radius term, r sub h, is in the numerator, meaning that as the observable universe expands, the radial expansion rate of the whole is increasing. That is, it is not constant, but is accelerating. Using the now and then approach, we see that the whole radius is expanding by a factor of 2 times the cube root of 2 with each doubling, matching the change in the radius of the whole discussed previously. And because the observable hyperverse is expanding at a constant rate, the radial expansion rate of the observable universe now to then is 1. So the relative expansion rate of the whole to the observable is 2 times the cube root of 2. So we have the problems of two velocities, and that the observable hyperverse is expanding at a constant rate of 2c, but the whole is undergoing an accelerating expansion with a vastly greater rate of 2c times r sub h over 2lp to the 4/3 power. Now we're going to review the small energy quantum, or SEQ, and the small radius quantum, the SRQ, both again of which were discussed in the geometric mean paper. The SEQ, or small energy quantum, is derived using the geometric mean counterpart of the energy of the observable universe. And like before, we take the energy of the SEQ, and we find if we multiply it by the energy of the observable universe, we get the initial energy squared. It's a geometric mean equation. And when we calculate out what the energy of the SEQ is, we find it to be c times h bar over r sub h. The SEQ, or small energy quantum, has an associated radius. We'll determine how many SEQs there are within the observable universe by dividing the energy of the observable universe by the energy of the SEQ. And we find this value here, r sub h over 2lp squared. We take the volume of the observable universe and divide it by this number, and we get this for the volume of an SEQ. And this factor, or portion of it here, is the radius cubed. So we take the cube root of this to get the radius of the SEQ, and we find it to be r sub h times 2lp over r sub h to the 2/3 power. And that comes to numerically about 6.5 times 10 to the minus 15 meters. The SRQ, or small radius quantum, is derived using the geometric mean counterpart of the radius of the observable universe. The SRQ, or small radius quantum, is derived using the geometric mean counterpart of the energy of the observable universe. We take our small radius quantum radius times the radius of the observable, and we get the initial radius squared. Solving for the small radius quantum radius gives us 4lp over r sub h, which can be also expressed as r sub h times 2lp over rh squared. And it comes to about 3.98 times 10 to the minus 96 meters. The SRQ, or small radius quantum, has an associated energy. The SRQ volume would be 2 pi squared times the SRQ radius cubed. So if we want to know how many units there are of SRQ within the observable universe, we'll take the volume of the universe, divide it by the volume of an SRQ, and we get that there are r sub h over 2lp to the 6th power units of SRQ within the observable universe. We use this value here for the energy of the observable universe, divided by the number of units of SRQ, and we get our term here for the energy of an SRQ. And it comes to about 2.77 times 10 to the minus 296 joules. Let us review how the SEQ and SRQ change with a doubling of the hyperverse radius using the now and then approach. Comparing the SEQ radius now to the SEQ radius then, when the universe was half its age, we find that the radius of the SEQ is increasing with a doubling by a factor of the cube root of 2, which is about 1.2599. The SRQ radius shrinks by 1/2 with each doubling. Again, we take our value for the SRQ radius now, divide it by the SRQ radius then, and we get 1/2. So it is shrinking while the SEQ radius is increasing. The relative size change of the SEQ radius to the SRQ radius then is the cube root of 2 divided by 1/2, or 2 times the cube root of 2. With each doubling of the hyperverse, the SEQ radius increases in size compared to the SRQ radius by a factor of 2 times the cube root of 2. Importantly, notice that this rate of change in the SEQ quantum level radius to the SRQ radius matches the rate of change of the radial velocity of the whole hyperverse relative to the observable hyperverse. Let's now review the ideal particle. In a previous paper, the paper on the origin of matter, we introduced the concept of the ideal particle. A particle with the target values of mass and radius that appears to be what the expanding universe is trying to create. Actual particles are somewhat different, assumably due to electrical interactions. Electrical interactions in hyperverse theory are believed to result from spin orientations. These are the equations of the ideal particle. And again, I'll refer you to the paper on the origin of matter for further detail on how these are calculated. But we get the ideal particle radius as the radius of the observable hyperverse times this factor here, 2Lp divided by r sub h to the 4/3 power. Particle mass is equal to the mass of the observable universe times that same conversion. And the number of ideal particles would be r sub h divided by 2Lp to the 4/3, which is about 10 to the 81. The SEQ frame advance. This is a review also. In an earlier paper, we discussed the concept of frame advances, in which the radial advance of the hyperverse can be described as occurring in incremental steps, or frames, each frame advance equal to the radius of either the SEQ or SRQ. To calculate the number of frames at the SEQ level, we take the radius of the observable hyperverse and divide it by the SEQ radius. So we take r sub h divided by the small energy quantum radius, and we get r sub h over 2Lp to the 2/3, or about 4 times 10 to the 40th. That's the number of SEQ frame advances. The time for the hyperverse to make one SEQ frame advance is the age of the universe divided by the number of SEQ frame advances. So we take the age of the universe divided by our r sub h over 2Lp to the 2/3 power, and we find that we get the SEQ radius divided by 2c. An SEQ frame advance currently takes about 10 to the minus 23 seconds. So we take our SEQ radius divided by 2c, and we get about 1.08 times 10 to the minus 23 seconds. Notice that the hyperverse radius, r sub h, is in the numerator, so that the time for an SEQ to make a frame advance increases as the universe expands. Using the now and then approach, we find that the time to make a frame advance increases at a rate of 1/2 the rate of the radial distance. That is, we take the time for the SEQ to make that frame advance now to then when the universe was half its age, and we get the cube root of 2. Now we can look at the SRQ, the small radius quantum frame advances. We determine the number of frame advances at the SRQ level similarly by dividing the observable hyperverse radius by the radius of the SRQ. And we find that there are R sub h over 2LP squared frame advances for the SRQ. The time for the hyperverse to make one SRQ frame advance is the age of the universe divided by the number of SRQ frame advances. So our age of the universe divided by R sub h over 2LP squared gives us the radius of the SRQ divided by 2c. And that's 6.6 times 10 to the minus 105 seconds. This is the value we defined as small time in the geometric mean expansion of space paper. We will now show that the acceleration of the whole hyperverse is canceled by the increase in the duration of the SEQ-based quantum of time. We showed earlier that with each doubling of the hyperverse radius, the whole radius is expanding faster than the observable radius by a factor of 2 times the cube root of 2. And we showed that with each doubling of the hyperverse radius, that relative to the SRQ radius, the SEQ radius also increases by a factor of 2 times the cube root of 2. Let's look at times now. Comparing the time for an SEQ frame advance against that of the SRQ, we find that the SEQ frame advance time increases at the following rate relative to the SRQ. We take our SEQ frame advance time divided by the SRQ frame advance time, and these are our values, and we get R sub h over 2LP to the 4/3 power. This equals the rate that the radial velocity of the whole increases relative to the observable hyperverse. So we take our value for the radial velocity of the whole divided by the radial velocity of the observable universe. We have this massive expansion rate for the whole divided by our constant 2c expansion rate for the observable, and we get that same value, R sub h over 2LP to the 4/3 power. Here is the key point. Both the radial velocity of the whole hyperverse relative to the observable and the frame advance time of an SEQ relative to the frame advance time of the SRQ are increasing at the same rate. Their identical rates cancel, leaving us with the constant expansion velocity of 2c. We are accustomed to thinking of time as a constant, but we see that in the accelerating whole hyperverse, the SEQ frame advance time increases with expansion. That is, this unit of time is not a constant. We can express the frame advance time in terms of time, using the relation that the age of the universe is this. We'll let t equals the age of the universe, so that t is equal to R sub h over 2c. We can rearrange so that R sub h is equal to t, or the age of the universe, times 2c, and we'll replace our RH term with 2 times 2c. So, we find that the SEQ frame advance time, which is our SEQ radius divided by 2c, and when we make the substitution here and plug in our values for the Planck length, we find the cube root of the age of the universe times g times h bar over c to the 5th, which happens to equal the age of the universe times the Planck time squared to the 1/3 power. So the SEQ frame advance time can be expressed as the cube root of the age of the universe times the Planck time squared. This time value is based on the ideal particle mass and radius, and would vary according to the structure of the specific particle. Thus, we could see this as the ideal particle quantum absorption time. We will now show that this time, the SEQ frame advance time, is the same amount of time it takes for a particle, an elementary particle, to absorb an SEQ quantum of energy. And we're going to use our ideal particle. The energy of the ideal particle is this value here, C times h bar over r sub h, that's the SEQ energy, times this factor here, r sub h over 2lp to the 2/3. The number of SEQ within the ideal particle then is the particle energy divided by the SEQ energy, and we get our r sub h over 2lp to the 2/3. Notice that this value matches the number of SEQ frame advances, suggesting a particle of matter absorbs 1 SEQ per SEQ frame advance. We can calculate the rate at which SEQ are absorbed by a particle by dividing the total time by the number of SEQ in a particle. So we'll take the age of the universe and divide it by the number of SEQ within a particle. And we find that's the radius of the SEQ divided by 2c. And that calculates out to about 1 times 10 to the minus 23 seconds. Now we're going to look at the relation of our SEQ absorption time to Piero Caldirola's chronon. Piero Caldirola produced an equation for the unit of quantum time for the classical electron. He called this unit of time the chronon. And this is a reference to a paper written by Farias and Rakami. And they review and extend Caldirola's work. The equation for Caldirola's quantum unit of time, given in the Rakami paper, is this value here. It comes to 6.26 times 10 to the minus 24 seconds. And this is very close to our value for the SEQ absorption time for the ideal particle, which is about 1 times 10 to the minus 23 seconds. Caldirola determined quantum time for the classical electron, whereas our SEQ absorption time is for the ideal particle. So let us insert the ideal particle mass into the Caldirola equation. Convert from classical to Compton radii by using the fine structure constant, and we'll modify the fraction in the Caldirola equation, changing it from 2/3 to 1/2. Small change here. So what we've done here, we've taken, this is the original Caldirola chronon equation, and we've modified it. We've changed this fraction to 1/2. We've added our value for the fine structure constant. And so it makes a slight change, going from 1/6 to 1/8 with the fine structure constant added. Inserting the value of the ideal particle mass into this modified Caldirola equation gives us the identical amount of time as the hyperverse's SEQ absorption equation. We get the 1.08 times 10 to the minus 23 seconds using this modified Caldirola equation. So we have an identity. The modified Caldirola equation and our hyperverse SEQ absorption time. Very different equations giving the same amount of time. So let's insert the ideal particle mass here into the equations up here and solve. And very interestingly, we get the correct equation for the electric charge. The square root of this value here. And we can do this differently. We can also use the mass of the electron in both the modified Calderola equation and our SEQ absorption time equation. Using the electron mass in the modified Calderola equation gives us a time equaling 6.44 times 10 to the minus 22 seconds. Using the hyperverse equation with the Compton radius of the electron, we find the same time interval, 6.44 times 10 to the minus 22 seconds. The modified Calderola equation gives the same value for the quantum of time as does the hyperverse model's SEQ absorption time. And equating them gives the correct equation for the electron charge. These are important results supporting the validity of the equations. Now we're going to look at how the quantum time and energy of a particle fit the time-energy uncertainty relation. Notice in this equation from a couple of slides ago that we take the Compton radius of the electron, divided by 2c, and we get h bar over 2 times the mass of the electron times c squared. But mc squared here would be the energy of the electron. That is, we can express the quantum absorption time as h bar over 2 times 1 over the energy of the particle. So this equation that we just looked at can be rewritten such that we just move this over here, so that h bar over 2 is equal to absorption time times the energy of the particle. And that's the time-energy uncertainty relation, where h bar over 2 is equal to the time times energy. We used the time-energy uncertainty in the geometric mean paper to argue that the universe is undergoing a geometric mean expansion, and here we find further support for that claim. Now, since we are dealing with the quantum levels themselves, we have no need of delta values. These are the delta values. So we can easily calculate the SEQ absorption times for the various elementary particles using the time-energy uncertainty relation, where the absorption time is equal to h bar divided by 2 times the energy of the particle. And this table is from the paper. I'm not going to go over it in too much detail, but all we did was take the energy of the various elementary particles, electron, muon, tau, and up and so forth, all the different levels, and calculate these values of time. Now this row here, this is our ideal particle, and these are the actual particle times. And you can see they're all a little bit above or a little bit below our ideal particle. The average is very close to this. Time, matter, and gravity are all related. Time, matter, gravity, and the quanta of energy are all related. We can state that a particle of matter absorbs 1 SEQ with each SEQ frame advance. Thus, the time it takes for a particle to absorb an SEQ is the SEQ frame advance time, about 10 to the minus 23 seconds, depending on the particle. We are made of elementary particles and atoms. Our time is atomic time. The model says that a particle of matter is altered with every SEQ frame advance. That matter is changed in quantized increments by the absorption of a quantum of energy with the passage of each unit of quantized time. We will propose that it is the absorption of a quantum of energy by an elementary particle in this unit of quantized time that forms the foundation of quantum time and quantum gravity. Gravity is the absorption of quantized energy by matter. The time it takes to absorb a quantum of energy matches the frame advance rate of the SEQ and gives us our unit of quantized time. We claim that the quantum unit of time is the time it takes for a particle of matter to absorb a quantum of energy. Additionally, the length of a unit of quantum time is not constant, but expands in duration with the expansion of the universe. This growth in the duration of the unit of quantum time is what gives us the constant 2c radial expansion rate of the hyperverse. And it supports the conjecture that the whole universe is indeed about 10 to the 243 times larger than the observable universe.